talked about how to go between an exponential and the log, and how to graph a log, which our strategy was to change it to an exponential. I know, I wish I could read something, but it's like up at the top. Yeah, that's fine. Sorry, you can scoot over. So we talked about if we wanted to graph it, we change them to exponential, and then we can draw a graph from there. I want to start off today looking at some equations. So if I asked you to solve this equation, do you have any ideas? Turn it into an exponential. Remember, the base of the log is the base of the exponential. So I'm going to start here. So it's 3 to the second power equals 4x minus 7. And this is something we should be able to solve. 3 to the second is 9 equals 4x minus 7. Add over 7. Divide by 4, and we get 4. One thing we are going to have to do on these is check. We talked about yesterday. The answer to a log is the exponent. So this 2 is an exponent. That is the only thing that can be negative. When we're talking about exponentials, it's always a positive number raised to a power gives us a positive answer. So with our logs, the base has to be positive and the argument has to be positive. So when I say check, all we're verifying is if I put a 4 in here, do I get a positive answer out? Yes, so it's okay. If that did not give me a positive, then I would say no solution. So what we have to remember is the argument, the thing we're doing the log of, has to be greater than 0. So you're doing a quick check for that. Let's look at B. Log base x of 64 equals 2. So if we change it into exponential, that would be x squared equals 64. How do you get rid of a square? And when we add a square root, so x is plus and minus 8. But we need to check. On the log, the argument and the base both have to be positive numbers. So do both of these answers work? No. The negative 8 does not. So 8 is our only solution. Is that okay? Let's look at some more. So log base x of 16 over 9 equals negative 2. So if we change this to exponential, it means x to the negative 2 power equals 16 over 9. Okay. What would we do from here? Okay. A negative exponent means 1 over x squared equals 16 over 9. Now what? So you said to make it a negative. So basically undo where we're at because you don't like having the x on the bottom. Let's talk about some of our different options. One option, if we just stuck with where we're at, could we cross multiply? So then we would have 16x squared equals 9. Divide by 16, so x squared is 9 over 16. To get rid of a square root with that, plus and minus 3/4. Are both of those possible? Nope, so 3/4 is our only answer. I don't want you to think that x can never be negative. Could the original problem have been log of base opposite of x? Sure. So don't just assume that negative answers never work. Another way of solving this problem we know we can take each side to a power, right? What if I did the -1 power on each side? -1 times -2 is +2. What would a negative power do to this? And then we can square root and get to the same point. So a couple different options there. Okay. Why don't you guys see if you can get B and C to work? I don't know why my log. So the first one you have 16 to the 3/4 equals x. That means the 4th root of 16 cubed. What's the 4th root of 16? Oh, you can cube first. I did the 4th root first. 4th root is 2 and 2 to the 3rd is 8. But you could do 16 cubed first and then the 4th root. Did you guys get 8 for that answer? Alright, this one we have 36 to the x equals the square root of 6. So we have to get a common base. 36 is 6 squared. A square root is like what power? So we have 6 to the 2x equals 6 to the 1/2. Remember solving these last week? So 2x equals 1/2. Divide by 2 and x is 1/4. Alright. Are we doing okay on those? Do we need more problems like this? Next thing we need to do is write down some properties of logs that we are going to be using today and tomorrow. So, all of these require your variables to be positive. So x, y, and a are all positive numbers and a can't be 1. Then, the product property says if you have the log of things being multiplied, you can add individual logs. Quotient, if you have logs of things divided, you can subtract the logs. The power property, exponents come down in front and condense our logs. Expand them, we can take one log and break it into multiple ones. If you have things being multiplied in your argument, each individual one do the log of and then add all those logs together. When we have things being divided, it's the top minus the bottom, log of the top minus log of the bottom. If you have multiple things on the bottom, each one of those gets subtracted off. Power property says if you have x to a power, those exponents can come down in front of the log and turn into a coefficient. All of this stuff is related to exponent laws. Think about if I said you had z squared times z to the fifth. What do you do with those exponents? Add them. So if we have the log of things being multiplied, we add our logs. If I said you had z to the fifth over z squared, what do we do with those exponents? Subtract them. So that's why we subtract our logs. Couple other things, which if you don't remember these as properties, it's okay. Log base a of 1 equals 0, and log base a of a equals 1. If we just remember our exponent rules from yesterday, if I said like log base 5 of 1, that means 5 to what power would equal 1? 0. So we don't have to necessarily memorize it as a rule. If we understand our logs, we know what they mean. If I said log base 5 of 5, 5 to what power equals 5? 1. So that's why those laws work. So let's practice using these properties a little bit. And we'll start with a couple more basic ones. If I ask you to evaluate these without a calculator, so log base 8 of 2 plus log base 8 of 4. You might be able to do your individual logs. Log base 8 of 2 means 8 to what power equals 2. You might know that. 1/3. If you didn't know that, if these logs are added, is there a way to combine them into 1? Yeah, if you want to put them into 1, we take these arguments and do what with them? Multiply. So that's log base 8 of 8. So 8 to what power equals 8? 1. Alright. This one, we probably do not know 6 to what power equals 18. It is not nice. But if I have two logs being subtracted, then if I want to put them together, what do we do with these arguments? Divide them. So I'm going to do 18 divided by 3. The 3 is on the bottom because that's the one that has a subtraction. So 18 divided by 3 is 6, and log base 6 of 6 is 1. Final two properties for today. We said yesterday that the logs and the exponentials are inverses of each other. Remember, inverses cancel one another out. So if we have both a log and an exponential, they cancel one another. So a to the log base a of m power equals m. And log base a of a to the r equals r. I wanted to give you a little justification for why these are true. If I said, let's use numbers. 5 to the log base 5 of 7 power. Okay, if we wanted to work this out, we don't know what it equals. So we talked yesterday about saying it's equal to x, right? Over here we have an exponential. We can change an exponential into a log. The base of the log is the base of the exponential. The log base 5 of x equals my exponent, which is log base 5 of 7. There's a log on each side, so they essentially can drop out, so that tells me the x is equal to 7. So that's why we can say if we have a 5 and a log base 5, because the exponential and the log are inverses, they cancel each other out. And all we're going to get back is our argument. Next one. If I said log base 3 of 3 to the 5th. Okay, properties of logs, what can happen with that 5? It comes down in front, so that's 5 times log base 3 of 3. Okay, 3 to what power equals 3? 1. So 5 times 1 is 5. So when you have a log and an exponential, again, they're inverses, they undo one another, and we just get our argument back. Okay. Let's look at this one. So if I wanted you to simplify these things. 2 to the log base 2 of pi. Power. What's that going to equal? Pi. We have the same base on our exponential and our log, so they cancel each other, and we just get pi using those properties. Log base 0.2 of 0.2 to the negative square root of 2 power. Base of log and the exponential are the same, so they cancel each other. We just get that negative square root of 2. We okay with those properties? Last slide, we're going to start where we're picking up tomorrow, using our properties to expand our logs. So we will do just a couple today, pick up here tomorrow, and we'll give you guys time to do your homework. If I ask you to expand means break this into multiple logs. If you have the log of things being multiplied, how do we break them apart? Add. You have to write the log base 7 each time. So it's log base 7 of 8 plus log base 7 of 6. Make sure the base of your log looks like in subscript. Sometimes people write it and it looks like log of 78, which is different. So make sure I can read that. And do I know 7 to what power equals 8? No. 7 to what power equals 6? Nope. So that's as far as I can go. Now what if I had like log base 7 of 7? That would turn into a 1. I would expect you to go ahead and reduce that. Okay, log base 6 of 12 over 5. How do I rewrite this? Can we reduce either of those? No. first, let's rewrite this. Log base A. The fourth root of r cubed. I could write that as r to what power? Okay, I don't have things being multiplied or divided, so I can't break it apart there. What can I do? So this is 3/4 log base A of r. And D. This is all under a square root, so what kind of power is that? So this whole thing is to the 1/2 power. Let's go ahead and take that 1/2 to each. So you power to a power, you multiply. So that's r to the 3/2. S 2 times 1/2 is just 1 over t 4 times 1/2 is 2. Am I done yet? Okay. What do we do next? We have the top minus log of the bottom. Okay, is that all I can do? What else can we do? Okay, what do I need to do with the r and my s though first? Those are multiplied, so what do I need to do with those logs? Add them. So it's log base A of r to the 3/2. And you might have done that on the previous step, but if not, we do it now. Plus log base A of s minus log base A of t squared. So then all of my exponents come down. So 3/2 log base A of r plus log base A of s minus 2 log base A of t. You're not going to have any of these on your homework tonight. We are picking up with those tomorrow, but I kind of wanted to do a bit of an example there. Any questions so far? Heads up, we don't have school Friday. Thursday, we are going to have a quiz over chapter 4, what we've covered so far. So, it's kind of a lot of stuff. We're doing the logs right now. Remember last week we were doing the exponentials, which I think since we're using that for a lot of our logs, that'll probably be okay. The thing that you probably need to refresh the most is the first section, 4.1. Remember we were doing inverses and things in that section. It's been a bit. I'll probably do some review problems tomorrow, but do you guys care if I do one review problem today, so I'm not just throwing everything at you tomorrow? Tomorrow is Wednesday, day after tomorrow's quiz. Okay, so nice quiz review question. This would be probably the highest point value question on your quiz. Find the inverse of f of x equals x over x minus 3. Okay. How do we find an inverse? First step, we change the f of x to a y. Second step, we get x and y flip. What's the third step? solve for y. So if I so we get xy minus 3x equals y. I'm trying to solve for y. I have y in multiple places, so let's get them on the same side. What do you want to do? Subtract the xy. Okay, can I actually subtract those? So what do we do? GCF, we can take out the y. So y divided by y is 1 minus x. And we divide. So y is negative 3x over 1 minus x. Final step, instead of y, we write inverse of x. Okay. On these, I usually ask for domain and range for both the function and the inverse. Domain is easier to find than range. So domain of the original function. If I look back at the original, what's my domain? X can't be 3. So we write that as negative infinity to 3, union 3 to infinity. And remember, the domain of the function becomes range of the inverse because x and y flip poles. Okay, my inverse. What's my domain? Can't be 1, so negative infinity to 1, union 1 to infinity. And the domain of the inverse is the same thing as the range of the original function. Alright. We will do some more review problems tomorrow, but I want to do an inverse today, and I'll do another one tomorrow. So the assignment for today. Page 442, 14 through 30 even.